Okay, let's talk about energy in the form of heat. By definition, heat is an actual measure of temperature change. And the original definition of heat actually had to do with measuring the temperature change of water. In particular, upon heating up water, what was being observed is how much energy could actually be absorbed by water for it to increase from whatever initial temperature up to a temperature that was higher by 1 degree Celsius. And at the time, we're talking about 1800s, maybe 1700s. Um, we were basically looking at the temperature um, or the amount of energy required to raise the temperature of water by 1 degree Celsius for every gram of water. And this amount of energy was denominated as the calorie. And yes, this is the same calorie that you see in nutritional labels, and it had, ultimately is correlated to the amount of water that can absorb heat just so that its temperature is raised by 1 degree Celsius. All right, now that's kind of cute and all, but it's not very systematic in terms of what it is. So here's where the physicists actually kind of come in and give us a much more robust definition of what heat represents. And here what you can see is that there is a block of 1 kilogram mass that is being held, at a height of 43 centimeters by a pulley system, right? And when the block is let go, right, when this support is removed, the block starts falling down, and as it falls down via connection of the system, what happens is that this little propeller-like steer rod starts steering. And pretty much the idea is that as the block falls down, the steering motion of this mechanical pulley system ends up transferring the potential energy of the block falling down to the ground into kinetic energy, which itself is turned into heat. And that heat is what's being measured here with a thermometer. The amount of heat being delivered to the water will raise the temperature of water to some amount. And so what ended up happening is that from the point of view of physics, we know how much energy is being delivered to the water because of the equation that relates a block of mass m falling down by some given height, in this case 43 centimeters worth of height. And that equation is simply potential energy equals mass times the gravitational constant times h. And if you carry out that type of calculation, 1 kilogram, of mass for the block times the acceleration of gravity, 9.8 meters per second square, times the height in meters, 0.43 meters, so I basically changed the centimeters to meters, divided by 100. What you find out is that this equals 4.184 kilograms per meter square over second square. And the interesting thing about it is that this is exactly the amount of energy that it does take to raise the 1 gram of water by 1 degree Celsius. So in essence, the full-on containing all the SI unit value of energy, 4.184 kilogram meter square over second square, is basically the main unit of energy. We actually refer to it as the joule. So instead of having all the collection of units, the kilogram meter square over second square, we simply refer as all of that in terms of the joule. And because 4.184 joules is the energy necessary to raise 1 gram of water by 1 degree Celsius, ultimately the calorie is equal to 4.184 joules. So this is a nice little conversion that allows you to go from some, I guess, common units of energy to the more helpful ones, the SI unit, which is the joule. All right, now that's kind of nice and all in terms of the definition of the unit and where it comes from, but how do we actually calculate it? Well, there is something known as the heat capacity of something, which kind of measures how much heat a substance can actually absorb upon being heated, right? So you could have a little substance right here, you put in the hot plate and you start heating it up and introducing heat into that substance. The temperature change that happens upon the substance absorbing heat is represented by a relatively simple equation. Q right here represents the heat in joules to be more specific. That's equal to the mass of the substance in grams, and this is multiplied by something we call the specific heat capacity. I myself sometimes just use the symbol capital C without the SH, but the important part about the specific heat capacity is that it comes in units of joules per gram degrees Celsius. And so when you multiply the specific heat capacity by mass, the grams will cancel out. And on top of that, you're multiplying this by the change in temperature in degrees Celsius, so that the degrees Celsius will cancel out. And ultimately, multiplying mass by specific heat capacity by the change in temperature is equivalent to the heat of the substance in joules. So let me show you an example. Let's find out how much heat is absorbed by 50 mLs of water when you warm it up from 22 degrees Celsius to 50 degrees Celsius. Given that the specific heat capacity of water is 4.184 joules per gram degrees Celsius. Alright, so we start with this formula. And the idea right here is that we're dealing with water, right? And technically what we want is the mass of water. But we do know that for water, the density is equal to 1 gram per ml. And the density is a conversion factor that allows us to go from volume to mass. So simply put, the 50 mLs of water multiplied by 1 gram per 1 ml, which is the density of water, will basically tell you that the mass of water is 50 grams. Now, if you were dealing with a different substance, or if I gave you a different density value, then you will have to multiply the 50 mLs by whatever the other density value is in order to get the mass of the substance. Alright, but right here we have the 50 grams of mass of water, we have the 4.184 joules per gram degrees Celsius for the heat capacity, and the final temperature is 50 degrees Celsius, the initial is 22. So subtracting 50 and 22 from each other is the same thing as 28. So 28 times 4.184 times 50, if you carry out the calculation, that will tell you that the heat is equal to 5,857.6 joules. Technically, you want to go with 3 sig figs in this problem. Now the temperatures here, they look like they only have 1 sig fig. I meant to actually write the 0.0, which I kind of left off from the problem. But yeah, so I'm going with 3 sig figs in this particular example. Now, the one thing I want to highlight is that this is in joules, right? But you could also convert, if needed, the joules into kilojoules, and you do that by dividing this whole thing by 1,000, in which case the decimal point will be moved 3 positions to the left, and you'll end up with 5.86 kilojoules if you keep it in 3 sig figs. The other thing to point out is that the value of the heat is positive, and the reason it's positive is because you raise the temperature, and raising the temperature means that you are absorbing heat. Therefore, the heat is positive. Alright, but let's see what happens when we're dealing with water, once again, 35 mLs. And instead of heating it up, let's see what happens when we cool down the water from 83 down to 37 degrees Celsius. And since this is still liquid water, we're still dealing with 4.184 joules per gram degrees Celsius. Alright, so all we do is we input the mass of water. Remember, the density of water, unless told otherwise, is 1 gram per ml. So we're dealing with 35 grams of water, 4.184 joules per gram degrees Celsius for the heat capacity. Final temperature is 37 this time around, 37 Celsius, and the initial was 83. So the change in temperature is actually going to be a negative number, which when you multiply by 4.184 and 35, you'll end up yielding negative 6,736.2 joules. Once again, I'm going to stick to 3 sig figs for this particular example. Divide by 1,000 and you could rewrite the heat in kilojoules. Now, in future problems, I will probably specify to you whether I want it in joules or kilojoules. Just pay attention to what type of unit I'm asking for. But aside from that, the big point to be said right here is that the heat ends up being negative. And the reason it's negative is because the temperature is now decreasing. And a decreasing temperature means that your substance has lost heat. And that loss of heat is represented with the negative sign. So, having negative and positive signs for the heat is actually kind of crucial. It tells me whether you have decreased temperature or increased temperature, and if you swap those signs, that's a bad mistake on from my point of view. All right, so heat lost is cooling down of a substance. All right, let's do another example. See how this plays out. So we want to find out how much heat is going to be required to heat up 27 mLs of water and 10 grams of ethanol from this initial temperature to 50 degrees Celsius. And what we are being told is that the specific capacity of water is 4.184 and that of ethanol is 2.4 joules gram degrees Celsius. Alright, so the idea is that you have two substances present in the same flask. And so some of the heat will go to the water, some of the heat will go into the ethanol. So to find out how much heat this will require, we have to come up with two sections to it. We have to have a Q equals MCAT, so M times C times the change in temperature, plus a second MCAT, M times C times change in temperature for the second substance, and we have to add them together because the amount of heat is being distributed into these two substances. Not necessarily equally, but it is being distributed between them. The amount of heat that the substance absorbs ultimately depends upon the value of the heat capacity, with the substances with a higher value of heat capacity taking in more heat. Alright, so we have a mass of 27 grams for water. Heat capacity is 4.184. The change in temperature, the final temperature is 50 degrees Celsius. There you go. And initial is the 22 that's right here. Same thing for the second substance, ethanol. Final temperature is 50 degrees, initial is 22, its heat capacity is 2.42, and we have 10 grams of that substance. So what we do is we carry on the subtractions. 50 minus 22 will be 28. So we multiply 28 by 4.184 and 27 on the one hand. On the other hand, we multiply the 28 by 2.42 and 10. So the grams, the degrees Celsius are going to cancel out. You will end up only with joules. So you'll end up with two values, 3163 and 677. If you add them together, you'll find out the total energy in heat, in joules for the heat, 3840.3. Which, if I ask you to, you could change to kilojoules dividing by 1000 to get 3.84. All right. So let's stop the video right here, and we'll talk a little bit about the bomb calorimeter. All right, see you in the next video.